good afternoon, everyone. Welcome to the FutureCast, where electronics is headed, where electronics design, automation. Electronics design is headed through the eyes of the under 40 Innovators award winners announced this morning. These are the gentlemen seated to my left. I'm going to introduce each one and ask them to say a few words about the work that they do to get us started. My name is Mcgrath. I am the editor-in-chief of EE Times. I should mention that. Okay, so first off, we have John Arthur, research staff member and hardware manager at IBM Research. John.
Thank you. So I work in the brain-inspired computing group, and what I spend my time doing is designing chips that try to take inspiration from the architecture of the brain, so spiking neurons, low-precision synapses, and build those into making very efficient hardware. And I spend the other half of my time trying to create algorithms so that we can train those networks to do useful tasks like face recognition or picking interesting objects out of scenes.
Okay, thank you, John. And then we have Paul Cunningham, Vice President of R&D at Cadence Design Systems.
All right, yeah, so my stuff's not quite as cool as your stuff. I run the R&D group at Cadence that is responsible for what we call front-end digital. So that's the logic synthesis, design for test, high-level synthesis. So basically all digital compilation tools that start from Verilog, VHDL, or C.
Okay. Thank you very much. And then we have Douglas Densmore, Associate Professor at Boston University.
Hi, yeah, so I'm a professor at Boston University, and what my research does is we look at how we can design novel living systems that look a little bit like electronics. So years ago, I learned that what we could do is we could take gates and put them in the living systems like E. coli. So imagine NOR gates, AND gates, et cetera, and do computation about bioremediation, fuels, energy, et cetera. So my group makes software tools inspired by EDA to design these systems. So for example, we have things like a Verilog compiler that compiles to a circuit that goes into E. coli or goes into yeast. And then we can design circuits to do sensing and remediation. And then along the way, we design synthetic cell-free systems that go into microfluidics. So we kind of have a hardware, software, wetware, co-design paradigm where we design the DNA circuit, we design the microfluidic hardware to test that circuit, and we design the electronic interface that communicate with the microfluidic. So again, bringing those paradigms into design of living systems.
Okay, that sounds fascinating. And our next winner is Youngpan Liu, Associate Professor at Tsinghua University.
Thank you. Hi, everyone. I'm Youngpan Liu from Tsinghua University. I'm working on the emerging memory-based circuit design for the IoT applications. So the motivation using emerging memory is they have zero leakage power and very power efficient operation for the future artificial intelligence operations and other very exciting features. So we are trying to deploy those advantages of the emerging memory for the IoT applications. Okay.
Great. Thank you very much. And then last but not least, we have Sasikant Manapatruni, physicist engineer at Intel Corp.
Hi, I'm a research scientist at Intel. Okay. I'm a research scientist at Intel Components Research. In a single sentence, our group and my job is to figure out what's the device technology that can come after a CMOS transistor. So we're looking at a radical replacement of existing materials, devices, and circuits in order to make next 20, 30 years of computer manufacturing. So I'm actually an experimental physicist, but I'm here in a design conference because to do these new breakthrough experiments, we had to start coding from nothing. So we started coding the SPICE for spintronic devices, and we used those device models and SPICE in order to come up with new devices. And then we go back to the material scientists and ask them to ab initio build those materials. So I have a very dichotomy of my job. One part is to write the hardcore physics that runs new devices and materials, the quantum mechanics of things. And the other side is to manufacture using molecular beam epitaxy those materials. So we're really in the 1960s for the next transistor, and that's what I do at Intel.
Okay, terrific. Well, thank you very much. And once again, congratulations to all of you for the award. So obviously we have a group of a fairly young men in the design world, and we're going to be talking a lot about the future of design. But I think just to get things started, talking about what's going on right now, and I'm going to ask each of you to address the question of what excites you the most about what's going on with electronic design today. And I'm gonna start right here with John.
Thank you. So I'm excited that Moore's law is slowing, and this sounds bad, but it means a lot of opportunity for innovation. And I think in particular, a lot of opportunity for new domain-specific architectures. So not just tackling one application, but a domain of applications. In particular, I'm interested in low-power, embeddable neural networks, and I think we're going to see a lot more in that space on edge devices that can actually do something intelligent and make decisions, either about what data they send into the cloud or about who's there, should that person be there, security applications, things like that.
Okay, interesting. And Paul, what excites you most about what's happening today?
Well, I'd say for sure, I mean, electronics is still the number one thing that's changing our lives in every way, whether it's, move to mobile or IoT. So to be a part of that thing that is changing society the most, I mean, some of the stuff we're talking about now and that I see coming up is things I read as a child in science fiction books. So to me, that's amazing. And then as well, in the same way, a little bit similar to John, I think that creates a need for innovation. And I mean, I'm a computer scientist at heart, so from what I do with the compilers in digital EDA, I don't think there's any industry that has so many complex algorithms of all varieties in one single place. So it's kind of like an algorithmic candy store for anyone that loves that sort of stuff.
Okay, terrific. Doug?
Well, I think from my perspective, what I'm most interested in on some level is we talk about biologically inspired computing. I'm interested in computing inspired biology, so how computing principles might make their way into biology. So what's exciting to me about today is the fact that we're at a place now where I can rapidly build systems that integrate with electronics and rapidly iterate on those prototypes. Whereas years ago, if I wanted to do this, we'd have to write a whole software library. We'd have to get a whole set of custom-made embedded devices. We'd have to build a whole kind of testing ecosystem around that. I always joke that students come into my office and they're like, why do you have so many books? I'm like, because before there was the internet, we had to look at books for things. But now, young graduate students, young researchers can jump in, get off the shelf kind of embedded hardware, work with existing kind of new biological systems and start to merge the two and play around. So that rapid kind of design, build, test phase that's enabled by the current state of embedded computing is exciting to me.
Okay, terrific. And Young Pan?
Yeah. To me, I think new devices will provide a lot of opportunities for us. I think that will excite me very much because you can see that there's a lot of, with the slowdown of the Moore's law, and we have to use more new devices to create a more interesting system. We have new devices like memristor, non-volatile memory, flexible transistor, biosensor. So for the IoT application, I think in the future, we have a lot of opportunity and research or for the commercialize to make this hybrid system with new devices. So I think that will give us a lot of opportunity to make the innovations.
Okay. So the slowing of Moore's law has already emerged as something that's giving opportunity for innovation here. Okay, Saucy, same question to you.
I'm from Intel, so I have
Yeah.
to say something about that. Moore's law is a law of innovation, and I think Intel has many times, and others have many times spoken about it. Someone wrote a Nature article about it, is that as long as there's innovation, there's going to be Moore's law in one form or the other. But talking about technology, I think we are seeing two major inflection points. The first inflection is that the old type of physics running devices is not going to cut it, right? So there's a big chance for disruption with new condensed matter. You talk to condensed matter physicists, they talk about ferroelectricity, spintronics, and ferroelasticity. We have never used them, we haven't even touched them. So there's a big opportunity to do that. And one form of that is the quantum, right? Quantum provides you a completely out-of-box solution to extremely hard problems. So this is the flight to quality in terms of physics. Then there's the flight to quality in terms of mathematics, which is the emergence of hard CS algorithms. Machine learning is a form of that, right? So I think these two inflection points can make next 10 years extremely exciting.
Okay. Wonderful. And let's move ahead then, and I think we will start with Paul this time. What do you see as the biggest barriers to innovation, technical or otherwise, that the industry is facing right now?
Yeah, I thought about that quite a bit actually, and in the end, I came down to a kind of human answer. I mean, innovation in the end comes from humans, and I think we need to get the talent. We need to get the young talent in, the graduate hires, people with the fresh perspectives, the fresh ideas, almost without the baggage of experience that we've got to try to think out of the box. And I sense some headwind there. I mean, there are a lot of opportunities, especially in software, for great, talented young people. So to bring them into our industry and our community, that's a real challenge. And we've got to kind of step up to work out how to do that.
So you're saying to bring them into our industry as opposed to going into one of the many other industries?
Yeah, I mean, great companies like Amazon, Facebook,
Right.
Google, I mean, they have very, very attractive value propositions. But as I say, from the point of view of my career and my experiences, especially if you get into EDA and you look at the algorithms of compilers, it's a really exciting place to be. Mm-hmm. And so, yeah, we have to get that out there and to keep the talent coming in. Right. That's really critical to innovation.
Okay. Doug?
Well, I'll speak a little bit on this academic side. So I think a really interesting space in general to be is at the border of different fields, and I'm kind of an example of that. But if we look in academia and we look at how young faculty are promoted and what is metrics for success, you have to take a risk to do lots of these things. So in my case, I got my PhD at UC Berkeley in 2007, and I had to do a 3-year postdoc to switch into biology, and then devote the last 7 years to biology. So 10 years at a time where I need to be extremely productive. So I think one of the challenges is if we want to get academia to kind of move in these interesting spaces, is how do we incentivize junior faculty, productive young folks to take those risks? How do we incentivize the publishing infrastructure to recognize interdisciplinary research? So again, it's different than industry, which I think has a number of challenges, but from the academic side, it's really how to incentivize people to take risks and not kind of do the status quo.
Interesting. Young Penn?
Yeah, actually, I think the most barrier for the innovation, I mean, for product, I think, is how to satisfy the real requirement with the feasible technology and many constraints. Actually, the constraint includes in the cost, actually the human resource, actually the fabrication technology. For example, for the non-volatile memory, we actually cannot, very few foundry in the world now can fabricate such as Ferro memory, STD-RAM memory, ReRAM memory, which is used for both for product or academic research. So I think the problem is how to make the optimization under so many constraints get the best result. I think that's the design automation people can contribute. Yeah.
Okay, and Sasi?
Okay. So I spoke to Joe right after the morning talk, and we both agreed on one thing. I actually teach high school students for a physics Olympiad, and they get excited about software and machine learning. The difference, and I think you should answer the question, is you got to make this open source, and at least make it open source even for a startup. If I want to start a company doing EDA, the cost of the tools is sometimes that's where the innovation is not coming in, right? So I think you have to really have a thinking, like stop thinking bureaucratic corporate, which is don't let new people, rather have an open source platform that people can play in. And startups shouldn't pay the fees till they start making revenues. And that's how you get new people who will bring new ideas. And I think that's something, maybe you can do something about. The second thing is that there's winner take all now, right? The phones are all by two companies and things like that, which reduces, the plurality of efforts.
Yes. So addressing your first point, so startups would pay a fee commensurate with their size, or how do you?
No, after they make revenue.
I see.
After they make revenue.
Okay.
And I can say that there are no open source software as good as what Cadence sells or what other companies sell. So you have to think of how Android came out, and you have to give some to get some.
All right, very interesting. And John?
Yeah, I agree. I think cost versus risk is a really big problem, because if you want to make a new architecture, that's going to cost a lot of investment in people. Fabbing new chips is expensive. And then really, if you're making a new architecture, you need to build an ecosystem around it. And that's a whole additional gigantic cost that comes with a lot of risk, because if it's not adopted, then it just goes down the tubes.
Okay. All right, very good. Doug, I think we'll start with you on the next question, which is, what do you think electronic design will look like 10 years from now?
Well, again, I'm biased, so I think it's going to be some kind of hybrid interface. So, I mean, there are things that electronics do really well. People ask me, are we trying to build a Pentium or an Intel processor in a microbe? No, because silicon does computing much faster than biology, which can take hours or days. But biology can sense things that electronics can't, whether they're heavy metals in drinking water, your microbiome inside your gut, aspects of your brain chemistry. Those are things that biology can do well. So I think the future is going to be having electronics continue to do what it does well, and coupling it with systems, whether they be chemical, biological, mechanical, that do things well in that domain, and getting them to merge in a way that's kind of seamless. And so what this community can bring to that are the design methodologies that's going to enable that process to be rapid and replicable and archived. I mean, when I go to biologists, they're blown away by the fact that it seems strange to not write in a notebook at their bench. And like, if I tried to design a computer with a notebook, I definitely wouldn't be profitable. So I think, again, that's going to be really the future, I think, is these kind of hybrid kind of systems. I think that's a really exciting possibility. And again, keeping things doing what they do well in their domain and coupling them intelligently.
And you use the word replicable. Like, do you believe that this is something that can be kind of taken from one sort of domain to another? And
one of the big challenges commercially with biological design is that if I make a circuit or something that works to improve production of a fuel in a fermenter, works in my fermenter, and then someone wants to replicate that in their fermenter in Brazil or something. Now we have totally different conditions. It doesn't, so what did I make? I made something very specialized. So the cross applicability is really important in the domain I'm in. And again, this kind of goes to tools. Like, we're very used to that in electronics. Like, in general, at this point in our life cycle, if I make a chip, hopefully another chip works relatively similarly, minor manufacturing details and other things aside. That's not the same in these other disciplines. So it's very frustrating if you spend hours and days and years doing something, then you can't reproduce it. So that's going to be key to commercialize the technology I'm talking about.
Okay, excellent.
You got to yield.
Yeah.
You got to yield.
Young Pan?
Yeah. Yes, for this question, I think it's related to the innovation source. I think the innovation source for the 10 years later design have two aspects. One aspect from the application driven. That means, for example, the artificial intelligence neural network. You can see a lot of design automation problem and the research come from these applications. So I think that's one driven. Another driven, I think, is the device driven from the physical layer, because we have a lot of new devices. So these new devices, how to use this new device in the future system, I think that's another driven for the innovation. For I guess for the future, 10 years later's design, we can see a lot of application-specific design, as well as a lot of hybrid new devices system design. So I think that's two aspects for the future.
Okay. Sasi?
Specifically to electronic design, I think it may start looking less electronic and more spintronic or ferroelectric, and that change can happen extremely quickly. You know, when things fail, they don't tell you that I'm going to fail, and you have a sudden inflection to a new technology. So I'm both fearful and hopeful of that. The other thing for the design process itself is that we have to move away from design automation to a design. There is no design which is not automated. Right? So I think it becomes more and more natural that design automation starts thinking as a designer of the system itself.
Oh, okay. And John?
So there's really two tool sets that I want in 10 years. And one of them is, I have a bunch of data and some kind of workload that I perform on that data. Just providing that, then the tool can try to optimize an architecture for that, a chip for that, and work in that domain and be super efficient and super high performing. So, Paul, I'd really like that tool soon.
Right.
And second,
Coming
I'd
up.
really like a tool where I can just kind of program a beverage in yeast. That would be cool too.
Not sure about that one.
And what,
So I think you were asking about kind of
10 years?
where do we see in 10 years? I mean, so I did a EDA startup. I came straight out of school and I tried to do a compiler company. It was originally actually for asynchronous circuits. But so I remember pitching to investors and they said to me, so this was early 2000, they were like, why are you doing a tools company? He said, in the future, everybody will do everything in software, like on a CPU or an FPGA. So there's going to be like a few chips and that's that. Actually, at this point, I think not only were they wrong, but it was the complete opposite. So I think as we mature into your point about it's just design, within 10 years, I mean, almost everything is going to have its own custom chip. I think we'll bring the barriers down there. And we're seeing that more and more with this device diversity, that you will make a customized device for that market that you're going for. And it will be that easy, it will be that automated. The entry point, when designing a chip won't be much different than designing software. So I think in that area, the VCs were right 10 years ago. It's just that you'll still push a button and a chip will come out the other end. And it will be perfect for that end application. And because all the devices will be everywhere in everything that you touch, I mean, the exact form factor, the power, the performance, the area is going to need to be customized for that end application. But it will really happen. And there'll be not necessarily exactly what we're talking about, but this blurring of electronics into human and cybernetics and that kind of thing. I think we're going to move in that direction too. We're going to start seeing, I don't know if that's quite the same as bioinformatics.
No,
But
I think there's similarities.
yeah. And then, to Doug and it's actually the end devices, we're going to have a lot more diversity about what we actually manufacture to. Yeah.
And when you say that it'll be that easy to create a custom chip for every application, I mean, is that just a function of the improvement in the tools available to design them that you?
I think it's like it's three things. So yeah, the level of automation, the efficiency and the cost of the manufacturing process, especially if you're not going to the latest and most advanced node, that cost is going to continue to come down. And then thirdly, I just think that the end application, the end market. So if all you're doing is servers and laptops, then that's okay. But if every single device that you have in your home and on your person is connected, you can't do that all with one chip. So it's kind of those three things together.
Okay. Great. And this is kind of a related question, but how will the technologies that are emerging today impact electronics design in the future, say 10 years in the future? So Young Pan, I'd like to start with you on this one.
Okay. Yeah, for this question, my answer, I think, is yes. So I believe that most of the emerging technology will be used in the future, but maybe they are not used as what the paper say, the way to use it, but in different forms. For example, in the paper, we see that maybe all the flip-flop in a chip should be replaced by emerging memory, but actually for the product, maybe it's so expensive. The yield will be a problem. So maybe in future, some of them will be replaced. So I believe that emerging technology will definitely have a great impact for the future circuit design, but the form will be slightly different with the research paper.
Right. Of course. Isn't that always the way?
Yeah.
Okay. Saucy, same question.
So my job is to make that connection, right? The devices get invented in academia, and we then see how it maps to an Intel product thing. So one common feature is non-volatility, is the permeance. You put something in a device and that stays there. It has a very important disruptive role that it can play, is that hardware companies can now sell algorithms. So we not only sell chips, but the chips, because of the non-volatility, come with custom optimized way to do a K-means cluster or do an image recognition. So that changes the value, from the software-centered value chain back to hardware. That's one possibility. The other one is quantum. Quantum would provide methods for encrypting data and for solving problems that are traditional computer science considered to be unsolvable. So these two. The third one is the natural progression of technology. When you reduce the energy to switch something near the thermodynamic limits, so there's a limit called thermodynamic limit given by Landau, and if you have two states, it says that the minimum energy is kT, K being the Boltzmann constant. However, that's not a workable device because it's adiabatic device. So right now, CMOS is at 1 million kT or 100,000 kT. And we have ideas, one of our ideas is on archive, to get that energy down to 100 kT. That means you're getting closer to the thermodynamic limits. But what it means is that now your computer never makes an error inside. The programmer made an error, you pushed it off, but the computer itself doesn't make errors. But now we have to let computers be stupid a little bit. They start making error now and then. But remember, our cell phone receive bad signal all the time, but they still decrypt the information, right? So in fact, with Naresh Shanbag at Sonic in UIUC, we're studying how to correct for errors that we let the computers make. So I think error correction and noise tolerance will now percolate down to the hardware layer. So
Interesting. Okay. John?
So I agree that on the physical side, there's a lot of technologies that are being created now that are going to find their way into our PDKs and our chips, non-volatile ones. There's also some crazy research going on in academia where they're trying to, on one wafer, grow transistors and then just keep growing vertically. So much denser than anything we have today, without small feature sizes even. So those things may eventually find their way in. But there's also other technologies like machine learning and deep learning that are really finding their way into all industries or finding their way into EDA already. And also, neural networks are often much less sensitive to that kind of variation and they have kind of built-in redundancy. So if the devices become stochastic, it's not necessarily a big problem. In theory, in practice, I think your point about what we read in the papers doesn't always pan out.
Okay. And Paul?
Yeah, for sure. I mean, machine learning is going to change the EDA software industry, same as it's changing a lot of other industries. There's huge applications for it on the compiler side. In terms of what devices are emerging, I mean, how that's going to influence us. I think when you start putting chips in cars, when you start looking at autonomous driving, when you start imagining a world where everything is connected and everything is sensing, then we're gonna have to grapple increasingly. I mean, security is becoming a bigger deal. Privacy, personal privacy, and I think with that, as we start to look at that, the device level, and the ecosystem level, I mean, eventually it's going to come into things like regulation, compliance, more red tape essentially. I mean, we have a little bit of the luxury of the Wild West in chip and internet, and you track it forward 10, 20 years, the whole infrastructure that's not technical is going to start to play a bigger role, I think.
Yeah. Okay. Doug?
Well, I'll jump on the machine learning AI bandwagon again. So we talked about Moore's law in electronics. In biotechnology, there's a set of curves called the Carlson curves that talk about our ability to synthesize DNA, that's to write it, and sequence DNA, that's to read it. And those costs are going down. So what that means now is for the same amount of money, I can make double the number of things or triple the number, 4, 10x times the number of DNA. So the idea is I'm going to make lots of things, and I'm going to need to use learning to actually determine what I should make next. So again, that's going to be really important, and software and computing infrastructure that helps that is important. Not to mention the data. We talked today, the keynote was talking about, it's one thing to store the data, it's another to actually learn something from it. We need to do both. That's, again, extremely important in biology, so that flow is important. Another technology that I think is related to computing that I think is interesting with biology is DNA storage. You guys have heard about the fact that we can encode information in DNA, and that's many times smaller. That's actually, from a density standpoint, that will compete very favorably with semiconductors. And so the future will be, again, if we have these large vats of DNA information that's storing many times more things in a small container that I could store in a whole server farm, how we're going to interact electronics with that and reconcile the latency and bandwidth differences in the two paradigms. So I think those are going to be some interesting technological pieces coming that are going to need to come together.
Okay. Terrific. Well, I think that everyone will bring their own particular biases to this question, as all of these questions. But is there a technology or set of technologies that you think will have particular impact going forward? Maybe 10 years into the future. We'll stick with that theme. Saucy, is there anything that you see of particular note right now?
I think we just spoke about that, right?
Yeah,
Machine learning, right?
Machine learning and AI has come up quite a bit.
So there's a bit of group thinking going
Yeah.
on here, but things surprise you more often than not.
Mm-hmm.
I think the big story that has been missing since we want normalcy is the shift in computing that we need, is to go back to the good old voltage scaling, good old frequency. Remember, you could buy a twice a faster computer every year. That's really the rocket that took us off, right? Mm. So I think spintronic devices and the devices that we are really, we changed our mind every year over the last 7 years before we converged on the new device that we proposed, the MISO device. And I think in one form or the other, it has the potential to bridge the gap between the old style CMOS, Moore's law, and the gap towards quantum computing, right? So there is a big space. We don't talk about it because there's a big elephant in the room, which is the machine learning AI. But all of this is driven by hardware in the end, and I think that's a space we haven't, others haven't paid attention yet.
And when you talk about bridging that gap, I mean, what type of time frame do you think that bridge will be in place for?
So interesting thing, researchers always say 10 years, right?
Yeah.
But I think
the safe one.
Yeah, the safe one. But things are getting a little bit more antsy now. If you speak to somebody, a VC in Silicon Valley, he probably has his pet quantum company, and he also has a pet hardware company, which is going to be the next transistor type of thing. So it could be sooner.
Okay, interesting. John?
Yeah, so machine learning again.
Yeah.
Right? I mean, in the last 5 years, it's gone from toy problems to beating humans at many tasks. And we have no idea where it's going to go in the next 10 years, other than it's really useful. And so it's going to go a lot of places. And if we can build better systems and better ecosystems, it really can go all sorts of places. Mobile devices, cars, anything you can think of, it could go there. And we don't know how to do it yet, but there's no fundamental reasons we can't.
Okay. Paul?
Yeah, if I move away from the software side of it, I think to your Sassy about that gap, the kind of energy per compute. something that's getting more attention now, may become more mainstream, this idea of at least going to near threshold-based devices. So there's quite a few startups playing in that space. It's getting attention. I mean, in many ways, as we just shrink the transistor geometry size, the voltages are coming down so low anyway, even at nominal. So I think that's going to take an increasing role. And then there's, we talked, John, about kind of monolithic 3D, stacking the transistors. The other one that's even closer to the quantum, but maybe a little bit less, and this would be very much for server, cloud, network infrastructure, is this Josephson junction-based compute.
FlexGate compute.
So kind of close to 0K inductive type devices. I think that's interesting. I mean, it's still not mainstream by any stretch, but
you do see that potential.
yeah, I think for sure, and we'll find ways. And then the biological circuits, I think that's very intriguing. So I still have a lot to learn there, but for sure.
All right, Doug.
Well, I mean, that triggers a thought. I mean, if I'm going to get to this human biological computing interaction model, wearable electronics are going to be really key. Flexible, things I can throw away and things that are cheap. If I'm really going to make this distributed sensor network where we have individual biological systems sampling the environment, this kind of biological Internet of Things where I'm sampling the air quality here and the water quality here and the soil quality here and radioing that information back and having these communicate in that way, that needs to be cheap, disposable, extremely efficient in terms of power and energy. So all of those things are going to be important. It's not a particular technology. Whatever this community can do to get us to those price points and those technology nodes would be great. But again, I think wearable electronics would be fantastic. We talk about sensors that can not only sense all the bacteria that, we don't like to think about this, but you're covered in bacteria, interacting with that, and ways that we can look at human health issues around sampling saliva, sweat, tears, things like that.
Okay, and Young Pan?
Yeah. For me, I think for the IoT applications, the non-volatile memory will be very, I think, very promising technology to reshape the future of the IoT processor. Because currently we are using flash memory, which is very power hungry and actually slow. But I think in the 5 years later, we'll have like STT-RAM memory or ReRAM memory, which is not only used for the storage, but also can be used for computation, like using crossbar architecture to doing very efficient artificial operations. So I think when that technology will be available in the near 5 years, we have a lot of opportunity to reshape the future IoT processor. So I think that will be a very impacted technology.
Okay. All right. Excellent. Well, each of you has made an impact before the age of 40. And as you look ahead to the next generation of people coming up behind you, I mean, what are you expecting from them? And we'll start with John.
Oh, good. I get to go first.
Yeah.
Okay. So I think, being at a design automation conference, there are great tools. There are great tools to design chips that can compile everything down from very high level to very low level. And these are great tools, and we should keep them. And at the same time, for things like deep learning, there are really great high-level tools that all you need to do is provide your data and some architecture, and they can train it and give you good performance. But I would really encourage everyone to understand what you're using and why it works and how it works. Because if you don't, you're never going to go beyond it. You're never going to build the next thing if you don't understand how the tools that you're using today work.
Okay. Good advice. Paul?
For the next generation, like graduates, people coming out of school
people
right now.
coming out of school right now, 15 years from now. What do
Oh, hard work. I think in the end, the ability to innovate, your raw talent, of course, those are very important, but you got to work hard and have ambition. So want to achieve, aspire to make a difference, and so that kind of passion and perseverance. There's, I think, at least 50% of accomplishing everything is hard work.
Yeah.
So sometimes I feel, because the whole point of civilization is to make your life better and for quality of life to evolve. But as quality of life improves, that doesn't mean that you can sit on a beach in Hawaii. You've got to work. So I'd still tell people to be prepared to work hard and have ambition, you know.
Yeah. And Doug, you obviously are on the front lines. You know some of these people and see them on a daily basis.
Well, again, maybe it's easier said than done, but my message still would be to take risks. I mean, particularly if you're young. I mean, I don't know, maybe you have 10 kids and 6 mortgages and 20 cars. Probably not. You probably have the ability to take risks in your career, try new things. I'm not saying this to say I'm particularly outstanding, but when I started in 2007, I hadn't taken a biology class since high school, and I take a calculated risk that I thought that there was a chance to take EDA concepts into biology. Everything I do on some level is still influenced by that approach, whether it's logic synthesis techniques for biology or the automation of DNA assembly using dynamic programming. These are all things that came from EDA. So I still think if I would tell people, I would say, try to do something big, try to not do something incremental. Take the foundation of whatever you've been trained in and find people that need those types of skills in new domains. I think I would be really excited. I tell all these undergraduates when they're graduating, they seem very overwhelmed. Like, oh, what job should I actually just relax, just be excited. You have many options at your fingertips. So again, that would be my message is embrace the freedom that you have and take a calculated risk.
Okay, wonderful. And Young Pan, same thing?
Yeah. For me, my suggestion is the right direction is the most important thing. And once you find the right direction, you should work continuously on it. And I think you will be success. So actually, right direction, for example, in the circuit design domain, for example, if you are working on the CMOS circuit design, that will be very challenging because actually most of the excellent idea is invented by your previously people. But if you are working some new device design, actually you still have a lot of opportunity. So actually, in that case, if you figure out that the direction, if you choose the CMOS direction, it will be very hard. But if you choose new device direction, that will be much easier to be success. So I think the direction actually is the most important for me.
Okay, great. And Saucy?
So I started teaching 13-year-olds who are now 15, and I get to see their evolution. So I have slightly different, maybe we all agree, but some people think hard work is the core thing. I really think creativity. You have to keep your creativity alive, and then when you have the passion for something you created, the hard work and the good intentions, good skills come naturally. I think being creative is very important because now a computer can beat you at Go, chess, and it can fly an airplane and drive a car. The only way human beings are relevant is by being creative.
Yeah.
And the second piece is that talk to your teachers. Talk to the people who taught you when you were in high school and in grad school. These people are a really great resource in giving you, the kind of advice. We probably are too young, but these professors can really give you the right advice.
Okay, wonderful. We are running out of time, but really quickly, what is the most important lesson that you have learned so far in your career? Paul?
So, I guess I'll give a kind of commercial answer. So, I have a group now of over 300 people, and there's an English phrase you have. There's more than one way to skin a cat. I don't know if that's used in American much, but I think one of the things, I went from starting a company where you have a small group of people, you're all very the same, you all start together. If you really want to empower a large organization, you've got to really embrace that there are many different ways to innovate. There are many different styles of writing software, of getting the job done, and you have to kind of embrace that and really work with it. If you try to constantly force everybody to be the same and work in the same way, that's not the way to get the best creativity and the best productivity out of a large team. Kind of embrace the diversity, and it actually, took me a while to learn that. So if I could give someone some advice, I'd encourage them to embrace it quickly.
Thank you. And Doug?
I think my advice is always to try to not be the smartest person in the room, So if I was putting a team together, I'd like to find people that know more about something than me. So that's typically a piece of advice. Be humble, be ready to learn.
Okay, Young Pan.
Yeah, my suggestion is hot topic is not always the right choice.
Okay.
Maybe some, yeah, not a very hot topic, but with not so competition, you can easier
Right. Okay.
success.
Good. And Saucy?
The thing I personally learned
Yeah.
is that I have to take risk, but in terms of technical diversity. So I went from control systems to photonics to healthcare to spintronics, and that diversity actually, it really ties into what he was saying. Is that sometimes then you get to see, okay, these two areas collide here. Maybe there's something new. So that's my personal thing, being more diverse and always taking on the challenge for, even though you don't know anything about it, jump on it and take the challenge of new areas.
Okay. And John?
Yeah, so I actually agree. I think the most important thing I've learned is take risks, and sometimes problems are impossible. Time travel is a bad problem to work on, but oftentimes problems that are valuable and seem hard are not as hard as they seem, so go after those, because if you succeed, then it's really valuable.
Okay. All right, terrific. Well, we are out of time, I believe. So I just want to thank the panelists one more time, and thank you, everyone, for joining us today. So thanks, guys.